Now, fluid mechanics, chapter 11, we are talking about the hydrostatic. So mean the fluid, they are not in motions. Or we call them a fluid static. Chapter 12, we're going to talk about the hydrodynamics or the fluid in motion, right? So fluids dynamics. Just a different name to talking about the same. Now, first thing we need to know that is density, right? So we're going to define the density. Density, we use a symbol of rho. Density is defined as mass over the volume. Now we're going to do the first example here, which is the number 2 on the homework. Now we have the neutron star, right? One type of astronomical objects. And the typical mass of the neutron star is 1.4 times 10 to the 3. The size, I should say that. The size is about 1,400 meters. And the mass will be 3.6 times 10 to the 23. So we want to find the density of the neutron star. So what is the density of a neutron star? So we use the equation, the definition of density. Mass 3.6 times 10 to the 28 kilogram. And what is the volume of a star? Can anyone tell me that? If you know the radius, how can I find the volume of the star? Anyone know what's the volume of a sphere? Hello, can you hear me?
Yes, sir. The name of what, sir?
No, I said, what is the volume of a sphere?
Oh, the volume?
Yes.
4/3 pi r cubed.
Yeah, 4/3 pi r cubed. So therefore, I'm going to divide this by the radius, which is 14. Now, don't forget the cube there, right? Now, if you calculate that, what do you get? And multiply by pi, multiply by 4, divided by 3, and take a reciprocal of that. So if you calculate that, right, so you will get 3.13 times 10 to the 18 kilogram per meter cube. Good. Now it's very high dense, very dense. Density, right? Think about that. What this number said. If you draw a cube, they are 1 meter each. Then the mass of this neutron star material will be 3.13 times 10 to the 18 kilogram. So unimaginable in front of you. Now, next question, determine the weight of a penny in pound. It was made by the neutron star material. Now I'm gonna find it. Now, how are we gonna do that, right? We want to find the weight, right? The weight Right, so we're gonna find that. What is that? The mass is equal to density times volume. Now, so therefore, what is the mass of the neutron star? I mean, I'm sorry, the mass of this penny made by the material from the neutron star. Then I'm gonna multiply the density of this material and the volume. Now, volume of a penny is what? 360 millimeter per, I mean, cubic millimeter. Right? Am I right? Hello?
Yes.
Yes.
No, but you cannot cancel the cubic meter, right? So what you need to do, you need to convert the cubic millimeter to cubic meter. So what we're gonna do, no problem, right? So I know that 1 millimeter. Now I should say that what is that? 10 millimeter is 1 centimeter, right? So in other words, 1,000 millimeter is equal to 1 meter. Am I right? Hello?
Yes.
1,000 millimeter is equal to 1 meter. So I have to take a cube of that, right? In order to cancel this. So therefore, look like that I have 360 divided by 1,000 to the power 3. I'm gonna calculate that, right? So I have 360 divided by 1,000 to the power 3. And then I'm gonna multiply the density of the neutron star. So I get 1.13 times 10 to the 12 kg. But we want to find the weight of this material, right? Which is a penny. So the weight is equal to mg. So therefore, that weight will be equal to 1.13 times 10 to the 12 kg times the gravity in here, right? So we refer to gravity here, right? Which is equal to what? Which is equal to 1.11 times 10 to the 13 Newton. Are you with me? Hello? Hello?
Yes.
Now,
Yes.
but here it's, we know that it's in Newton, right? We need to convert them to pound. So I know that 1 pound is 4.4 Newton. You see the last bracket conversion factor, 1 pound is 4.448 Newtons. So I'm gonna cancel this, and then I'm gonna divide it by 4.448. So I get 2.48 times 12, right? So that will be the SI unit of, I mean, the British unit of the weight. 2.48 times 10 to the 12 pounds. Again, the size is unimaginable. The weight is unimaginable. You can think about it. If you make up a penny by the material in a neutron star, the weight is 2.48 times 10 to the 12 pounds. Extremely, extremely heavy, right? Okay. Now, then the next thing I want to talk about is the pressure. So first of all, I'm going to define the pressure, right? Now, what is pressure? Pressure is defined by force over the cross-section area. So let's say I have an area here. So I'm going to apply a force on that. Let's say I'm going to apply a force like this. Then what is the pressure? Now, the pressure will be the perpendicular component of the force. Let's say the angle here is theta. So therefore, the pressure here will be equal to what? I'm going to call it F perpendicular divided by A, where A will be the area of the surface. So in this case here will be F psi theta divided by A. So the point I try to illustrate that is the force, the area has to be perpendicular to the force in order to define the pressure. So you're not worried about applying force parallel to the surface, right? There's no pressure. Am I right? Hello? Right? Has to be perpendicular, right?
Yeah.
So if I apply a force parallel to the surface, there will be no pressures. Now, so therefore, I can write that as F over A, right? The unit for the pressure will be 1 Newton per 1 meter square. So we call them 1 Pascal or 1 PA. Good? Now, one thing is we experience the pressure every day, right? From where? Where's the pressure we experience every day?
The atmosphere?
The atmospheric pressure, right? What is the atmospheric pressure? Now, at sea level, right? So we are living in sea level in Houston, right? At sea level, the pressure at sea level, and we call them a ATM, right? Or you can put the Y equals 0, you know? So it's equal to 1.01 times 10 to the 5th Pascal. Or you can write it 101 kilopascal. Or you can write it in the unit you like, right? The British units, 14.7 pound per inch square. Or this thing we call the PSI. Get it? Hello?
Yes.
Now, that's another unit we use a lot, right? If you see the Weather Channel, where they said the mini bar and bar, right? What is bar? 1 bar is equal to 10 to the 5th Pascal. So they are approximately equal to 1 ATM or 1 atmospheric pressures. Here is 1 ATM, right? Now you see that always said that, right? The pressure, right? You're talking about a hurricane. Okay. A hurricane like this. So therefore, the air flew into a cyclone like this, right? Now, hurricane in general, they are low pressure system. Lower the pressure means higher of the string of the hurricane, right? So you always hear the word, right? Oh, the pressure is 980 millibar. Now, what does that mean? So you can calculate that from here, right? 980 millibar will be what? 9.8. What is that? 9.8 times 10 to the 2 times 10 to the minus 3. Wow. Am I right? Hello? Hello?
Wait, why are you doing times 10 to the 2 and then times 10 to the negative 3?
Milli mean 10 to the negative 3. Millimeter, right?
Oh, okay.
Can you also say, can you see?
Yes.
So therefore, that one is 0.98 bar, right? So I don't remember the benchmark, right? If you go lower than 940, 950, and then you better leave that place or you will die. You got it?
So there's no
you're
such
talking
thing as a
about-
like.
You're talking about the category 4 or even the category 5 hurricanes. Yes, sir.
Oh, okay. So you're never gonna see
Lower
like
the pressure
0.7.
means stronger the hurricane. The reason for that is they will rotate very fast. So if you lower the pressure low mean what? Pressure low mean that all the air flow in. when the air flow in, they suck up all the water, right? So hurricane is getting the strength from the oceans. And why the global, the climate change create a monster hurricane? The reason for that is the ocean temperature higher, then higher the temperature of the ocean, then you will feel the hurricane. The ocean like an engine, you know, the hurricane like a heat engines. We're gonna talk about it in the last 3 chapters in class. Good. Hello. Hello.
Yes.
Now then we want to understand this gauge pressure. Right? Now let's say that I have a block. So let's say I have a container, right? Easy to visualize that. We can talk about it in the ocean or we can talk about it in a lake. Let's say the length, the height of the block is H. The cross-section area is A here. Then the question is, I want to find the pressure at the bottom here. Now, what is the pressure here, right? Now, let's say the container is sitting open air. So therefore, you're gonna experience the atmospheric pressure. Am I right? And then you're gonna experience the pressure from at the bottom. First of all, I'm gonna look at the force first. Well, the force at the bottom, right? The force at the bottom here is equal to the force at the top from the atmospheric pressure multiplied by A. Am I right? Hello? So if you want to find the force by the atmospheric pressure, you just multiply by the cross-section area A plus the weight of this piece. Well, it's sitting here, right? So you have the weight of the blue color section there. Now, then what we're gonna do, so we're gonna calculate that. Now, what is the weight of that piece, right? It should be the mg, right? Good, hello. Hello, can you hear me?
Yes. Yes.
Now then, what is mg, right? Mg is that piece. Let's say that piece is just the water. Same thing as outside. So therefore, that piece will be equal to the density of the water times the volume of that piece times g. Am I right? Hello. Remember that you can write the weight, the mass equal to density times volume, right? Hello.
Mm-hmm.
Yes.
Now then, what is that volume equal to? The volume should be equal to A times H, right? A times H. The cross-section area times the height. And then G equal to F. Now, then what I'm gonna do, then I'm gonna divide both sides by the A, right? So I have F over A equal to PATM plus rho GH. But what is F over A equal to? F over A, you can say the pressure at the bottom right here. So in other words, we can write the pressure at any depth, any deep of the water. If you're diving in the water, if you go deeper and deeper, the pressure will getting higher and higher. Am I right? Hello?
Yeah.
Yeah.
So that pressure will be equal to what? That pressure will be equal to P minus PATM. We call them a gauge pressures. Which is equal to rho GH. What is rho here? If the fluid is water, then rho will be the density of the water. if the fluid is mercury, right, that will be the density of the mercury. Good. Now, this gauge pressure is have another meaning, right? Now, let's say that I'm going to discount tire. Now, you have a tire, right? Hello?
Yep.
Now, what is the pressure of the tire, right? I think it's 32 PSI, right? Or 32 to 35, right? Is that right?
I think so, yeah.
Depend if you have a sedan, I think so, you know. For the F-150, I don't know. Now, what does that 32 and 35 PSI mean? So the meaning of that is the following. Now, let's say that if your tire is sitting exposed in the air, so at any point, right, the tire will experience the pressure from the atmosphere. Am I right?
Mm-hmm.
So that will be a PATM. But I know that the tire inside, right, you pump the air inside, then the tire itself from inside, it have an inner pressure against this atmospheric pressures. And let's say this one is called P. So 32 to 35 PSI mean P minus PATM. The pressure difference between inside and outside. Are you with me?
Yes.
Now, then I'm going to ask you that, right? You know at Denver, right? Have you been Denver? Or they call the 3 Mile High City, right? Or Salt Lake City. So let's say that you're going to drive a car there. What happened to the tire? Assume that there's no air leak of the tire. If you drive a car, let's say I have a car, my tire sitting in Denver. Then what happened? Compare with the tire sitting in Houston.
Your pressure will go down. There's more atmospheric pressure.
The tire will inflate more, right? Am I right? The reason for that, if you go to the high elevation, the atmospheric pressure decrease. Am I right? Hello?
Yes.
So therefore, the gauge pressure increase, right? So it looked like the tire a buckle, right? Now, obviously, this effect is very small, right? The tire will buckle a little bit. Now, by the same token, right? If you go to Death Valley, right? You know Death Valley, right? Hello?
Where's that at?
It's in California, the border between California and...
Oh, right. Yeah.
Now, if you go to Death Valley, right? Death Valley is in here is high elevations. Death Valley is the lower elevation point in North America, I believe. Then the tire will flat a little bit. So in other words, if the original size is this, then in that value, right, a little bit. Now, obviously, I'm going to exaggerate, right? The effect is very small. But the point is, your tire gauge pressure depends on where, I assume that there's no air leak, right? Your tire gauge pressure depends on where you located. Now, with this in mind, right, with this concept of the pressure, we should be able to introduce the so-called Pascal principle. Now, what is Pascal principle? Now, Pascal principle say that the statement say that a change in pressure apply. So you apply the change of the pressure in a enclosed fluid. So the fluid inside an enclosed container is transmitted in diminish to all portions of the fluids and the wall of the container. Now, what does that mean? Now we can draw it here, right? Now I'm gonna draw some container. They're making a very interesting shape. I have a container like this. Now let's say you're gonna fill the container with some liquid. So my question to you is, what is the level of the fluid? So 1, same, 2, difference. So what is the answer? So the level of the fluid, are they same or are they different? Hello?
They're the same.
Why? Why they're same, right?
Well,
The
if you-
answer, yes, they're same, right? Now, the reason is we explained the Pascal principle. Pascal principle said that inside the container, the pressure will be same everywhere. So therefore, if you fill the water inside, they will be all in the same level. Same level. Yeah. Now, what is the application of Pascal principle? The Pascal principle said that if I apply the pressure should be same everywhere. So in other words, the very important application will be the hydraulic press or the jack or whatever. Hydraulic system, right? You can say that. So hydraulic system mean the input force or whatever, right? The pressure, input force is much, much less than the output. And we know that later on, right, we can define the efficiency of the mechanical system. So in efficiency, it defines what? Efficiency is defined as output divided by input. Good. So larger the efficiency, then you have a better, much better machine. Can do a lot of things. Now I'm going to draw a schematic diagram of a hydraulic jet, right? So very, I mean, what should I say there? Close. A simple way to draw that. Now I'm gonna draw that is like this. Now here I have a cylinder, right? You can think about that will be a master cylinder. Your braking system will be the same idea, right? A master cylinder. And then here I have another cylinder here. That one will be the slave cylinder, right? Or I would call the primary or secondary cylinder, either way, right? Now, what the hydraulic jack apply is the following, right? So we're gonna apply, they have a hydraulic fluid inside, right? Have you seen the hydraulic fluid before? Hello?
Yes.
The black fluid will be a hydraulic fluid, right? Have you seen the black fluid? You can buy in the O'Reilly or the AutoZone, right? Now, what they are doing is you apply a force here, and then you're gonna have another force coming out, right? Now, the idea to apply the Pascal principle here is I have A1 and I have A2, right? So A1, now the idea, the Pascal principle is F1, A1 equal to F2, A2. Am I right? Hello? The pressure, or if I write it in the same statement of the Pascal principle, will be P1 equal to P2, right? The pressure is same everywhere. So, but if you write this statement, it will be equivalent to F1 A1 divided by equal to F2 A2. Can you hear me?
Yes, sir.
So therefore, what is F2 equal to? The force on the jet, right? For F2 will be equal to A2 divided by A1 times F1. But one thing I know that from this diagram, right, the way I draw, the A1 is much, much smaller than A2. So in other words, A2 over A1 is much, much bigger than 1. So in other words, you will magnify your pi force by many, many times. Can you hear me? So it's just like that if you go to a mechanic shop, right, they jack up your car, right? They use a not very small, using the force from the motor to jack up the whole car, right? How heavy is the car? 2,000 kilograms, you know, at least. Right? Can you hear me?
Yes.
Now, I am going to look at the example here. We come back. Now, next section we want to talk about that we call the Archimedes principle. I think you might hear that in high school, I know. Now, what is Archimedes principle? Archimedes principle is all about the buoyancy or the flotation force. Flotation, right? You know there's a force. Good. Now I'm gonna show you some picture here. Now let's say that I have a container. Now this container have an opening. Now what I'm gonna do, I'm gonna fill the water very just at the end of the container. Right? Nothing happened, right? You know that. Hello?
Doesn't spill out.
No, no water fall out, right? Because see, they are just at the level of the opening. Unless you shake it, right?
Mhm.
Now, then what I'm gonna do is I'm gonna put a submerge an object inside. Then what happened? Then you have the display liquid, right? Overflow, right?
Yeah, it displays.
The
Displacement.
liquid will display to here. Now, this volume of the liquid, you can measure that, what we call the VL. So in other words, VL will be the volume of display liquid. And the VOBJ will be the volume of the objects. Now, what Archimedes principle said that is the following, right? Number one, so if the whole object is totally submerged, right? If object totally submerged, then the volume of the OBJ should be equal to the volume of the liquid. Good. Hello.
Yes.
Now, immediately you will have a very important application on that one. What is that? That will be this. Now, let's say that I'm gonna give you a piece of the moon rock. So how are you gonna measure the volume of the moon rock? Are you gonna use a meter? Are you a measuring tape to measure it? Hello? How are you gonna measure the volume of this moon rock? Hello?
Could
Put it in
you?
water.
Well, I
Yeah.
put it inside the water, right? I measure the water dissipated by this moon rock. That will be the volume of the moon rock. They apply to any irregular shapes, right? Any irregular shapes. Now, the next thing, important thing is, now I know that no matter whether my object is sink or flow, then we always have a force, upward force. We call the buoyancy force. So the buoyancy, let's say it's called FB. Now, according to Archimedes principle, this buoyancy force should be equal to weight of the displaced liquid. Now, what is the weight of displaced liquid, right? Will be the mass of the displaced liquid right here. Times G. Am I right? Hello?
Mm-hmm.
But what is the mass? I remember that from now on, when we are talking about the fluid mechanics, forget about the mass. Whenever you see the mass, you're gonna write it in terms of density of the liquid, volume of the liquid times G. Good. Density times volume equal to mass. But from one, I know that the volume of the liquid is same as the volume of the object, right? So that would be this. So in other words, we can quantify the buoyancy force by knowing, if you're knowing the density of the liquid, the volume of the displaced liquid, and G, then you know the buoyancy force. Now the question that is, we are going back to the Dead Sea, right? Why the buoyancy force is so strong in Dead Sea? You can look at it here, right? Why? What is the water in Dead Sea? What they are? What the difference between the water in the ocean than the water in Dead Sea?
Does it have to do with?
Now we know the Archimedes principle, right? Now we introduce another concept, then we're gonna go to do some example. Now here we have some term where we call it specific gravity. Now what is specific gravity, right? Specific gravity is defined as the ratio of the density of an object to a fluid. So usually the fluid here, we will use the H2O. Good. Now you have this the hydrometer, right? They are measuring the specific gravity. I don't know whether you see that hydrometer. So they look like following. They look like this image. Now, what they are using for, so I'm gonna, okay, this one. Now, what they are using for is somebody give you some alcohol. They said the alcohol content inside is like tequila, right? Tequila 20%, right? Is that right? Then how could you know that? Then
Yes.
you're gonna put this meter inside, but look at the reading there, then you should know that. And I believe the alcohol density is smaller than the density of the water. Then you see that reading is upon A, right? They upon A, then you know that that will be a tequila grade, right? 20% alcohol. You got it? Hello?
Mm-hmm.
So usually they are, as far as I know, that they use it to measure the alcohol content of the fluid of the liquor. Okay. Now what I'm gonna do right now is I'm going to, hello, 1,000 kilogram per meter cube. Now what we're gonna find here is the following, right? So what are they asking you? Determine the height of the the parallel pipe in the water. So we want to find H minus H naught. Am I right?
Mhm.
H minus H naught equal to what? Now, the first thing you have to do that, you have to find the H naught, right? Am I right? If you know the H naught, then you know the H minus H naught. But that's the point here. Now, then how are we going to do this problem, right? Now, the way you're doing this problem is what? The way you're doing this problem is you're going to use the hydrostatic, right? Fluid static. So what I said is I'm going to sum all the force in y direction equals 0. Am I right? Hello, can you hear me? Can you
Yes.
hear me?
Yeah.
Now then, H minus H naught is just same as HW, right? But look at this diagram here. It's okay. Now then I'm gonna draw a free body diagram here, right? First, I have the force of the weight, which is mg. Make sense? Hello? Hello, can you hear me?
Yes,
Yes.
sir.
Now then I have the buoyancy force, right? How many buoyancy force we have here? How many buoyancy force we have here?
Is it 2?
2, right? One is from the oil, one is from the water, right?
Yes.
Now then I would say that FBO, and then I have another one that FBW or FBH2O, right? Another one will be FBW. Good. Now they should be equal, right? So in other words, so I have FBO plus FBW minus mg equals 0. So therefore, now I'm gonna leave it like that, right? So the question is, what is FBO? Remember, the buoyancy force is what? The density of the liquid. Here will be the density of the oil times the volume of the object, right? So I'm just trying to remind you, right? The buoyancy force, you can write a density of liquid, volume of liquid times G, or you can write a density of liquid, volume of the object submerged times G, right? Either way, right? Can you hear me?
Yes.
But by look at the oil part, right? What is the volume of the oil part? The volume of the oil part will be equal to what? Now I'm gonna write it V OBJ in the oil times G. Now I'm gonna write it out, right? Now what is the volume part what is the object volume in the oil? Should be D squared times HO. Am I right? Hello? The area times the height, right? Hello?
Yeah.
And then multiply by G. Now then I'm gonna do the same thing for the water, right? So FBW will be the density of the water times the volume of the object inside the water, right? That will be equal to what? D squared times HW times G. Am I right? Hello?
Yes.
Yes.
Now, so therefore, so what can I write? So therefore, I can write the FBO plus FBW. So density of the oil, D squared HOG plus density of the H2O times D squared HW. Now this one is not homework, right? You know that. It's H sub W times G equal to mg. Am I right? Hello, can you hear me?
Yes, sir.
Now, you know that it does not depend on the G, right? So you can see that if I take this experiment, do it on the surface of the Mars, the result will be the same. The G cancel out. Now then I'm gonna put all the number in, right? So we are solving for HO. Eh? So I already have all the number. Oil is 710. And D is 0.25. And HO is the unknown. Plus density of the water 1,000. And then 0.25 square. HW is, what is HW? Do we know HW? Well, we don't know HW, right? That's fine. I know H. Well, what is HW? Well, you can write the HW is equal to H minus HO. Am I right? Hello?
Yes.
We are looking for the, but it's okay. They are actually the question. I find the height in the water. Right? It's okay. We found the HO. We know the HW. No problems. Now, so therefore, I'm gonna write my HW as H, which is 0.12 minus HO. Good. Hello. Can you hear me?
Yes, sir.
That will be equal to the mass of the block, which is 7. Now then I'm going to solve it, right? So I have 0.25 squared times 710, which is 44.375 HO. Plus, I have 0.25 squared times 1,000, which is 62.5. And then time 0.12 minus H0 equals 7. Now then I'm going to collect all the term in the H0, right? So I have 44.375 H0 plus 62.5 times 0.12, which is 7.5, minus 62.5 H0 equal to 7. Am I right? Hello? Can you hear me?
Yes, sir.
Now then we have 0.5 equal to 62.5 minus 44.375, right, which is 18.125 H0. H oil. H oil will be equal to 0.028 meter. So therefore, what is the water part? Well, you subtract this by the water. So therefore, the HW will be equal to H minus H oil, which is 0.12 minus 0.028. Good. Will be 0.092 meter. Good. Can you hear me?
Yes, sir.
Now, the idea for this problem is, as the title of the chapter, hydrostatic. The force on the object, no matter how many layers they have, it should be equal to 0. They are in equilibrium state. Right? Okay. Now, then the next thing, any questions so far? Am I going too fast? Now, next thing we're talking about is wetting. Now, I don't know whether you know that, right? Let's say I have a your fall, right? If you put a water there, what does that water look like? Am I right? Hello?
Yeah.
Now, if you put it in a piece of wood, then what's the water look like?
It gets soaked up.
They get soaked up, right? That will look like this. Now, there's something we are calling in the material science or whatever, mechanical engineer, right? Or they call the wetting, right? What is wetting? Wetting is the ability of a liquid to maintain contact with a solid surface. And resulting from the intermolecular interactions. Now, it's something to do with the molecule interaction between the plastic and water, or the molecule interaction between the wood and the water, right? Now, in general, we have two types of wetting, right? We call it hydrophobic. Now, you know what phobic mean, right? Hello?
To repel?
Hydrophobic mean they repel the water, right? Or claustrophobic mean you're very scared about the closed space, right? Or another one is called a hydrophilic, I believe. I don't remember how to spell it. So mean they like the water, right? Good.
Yes.
So obviously the new flatbed from the new shirt right now, right? You know what I'm talking about? You know that, let's say 10 years ago, right? So I'm gonna show you my camera first. Okay, can you see my hand? No. Yeah, I'm gonna change the camera. You see my table, right? Hello?
Yes. Yes, the cameras.
Now, let's say 10 years ago, right? Or some years ago, you don't have this type of flatbed, right? They are, what type of flatbed? They are hydrophobic or hydrophilic?
Would it be hydrophilic?
Yeah, with a hydrophobic, right? They don't have stop that. They drive very fast. You don't feel uncomfortable in the summer, right?
Oh, okay.
And something like the Under Armour too, right? I think as a matter of fact, this one is Under Armour.
Oh, because of the material?
Yeah, the material, you don't find this type of material, say 10, 15 years ago. Now you go buy some garment, right? They have very, what should I say? If you go to the TJ Maxx and doing a treasury hunting, right? You find something there. The fabric is very different. You touch it and you feel that. Well, there's something to do with how they create this type of material. They are hydrophobic or hydrophilic. And when you wear that, you feel very comfortable. Right? Is that right? Hello?
Mm-hmm. Yeah.
Okay. Now I'm gonna turn on my camera. Now then, this wedding, right? If you look at very deep, right? They depend on what? They depend on several factors. One is the hydrogen bond of the material itself, right? The water hydrogen bond. Another one we call the ions induced dipole force. Right? There's something to do with the dipole force. Another one will be the ion dipole force. Now we're going to talk about a dipole force in 1308, right? And the last one, right, depend on whether they wet is the van der Waals force. Now you should see that, right? We're taking a chemistry, right? Hello?
Yes.
The intermolecular force, right? Something like that, right? The van der Waals force, and then we have different type, right?
Yeah, there's 4, I think.
One is called a Keeson force. Another one is called a Debye. Another one is called the London.
Yeah, London.
Dispersion. Oh, you saw that before? Not the city of London, right? London is the name of some scientists last century, okay? Anyway. Now the degree of the wetting, right? So how wet, how the liquid can wet the surface, right? We call the degree of the wetting. So we call the name of that, we call the wettability. Wettability. Or its degree of wetting. Good, hello?
Yes.
Now, this degree of wetting or the wettability is determined by the force balance, right, between the cohesive force. Now, I'm going to show it to you, cohesive and the adhesive force. Now, what is a cohesive force, adhesive force? Right? You can think about a cohesive force is the attracting force between the same molecule, right? Same type of molecule. Now, what is adhesive force? Right? Adhesive force will be the force between, which I should say the attracting force again, right? Between the different type of molecule. You got it? Hello?
Yes.
Now, I'm going to give you some example. Right? I don't know whether you see that before. Right? Let's say I have a cup of water. You can go and look at it when the class over, right? So if you look at the water level, they look like this. Am I right?
Mhm.
Am I right?
Yeah, it's not like a perfectly straight line.
Yeah, they wet, right? Actually, they wet the glass, right? You can think about it. So what does that mean? It means that the adhesive force here, adhesive force, the adhesive force here is larger than the cohesive force. So in other words, the force between the H2O and the glass is larger than the force between H2O and H2O. You got it?
Okay.
Hello?
Yes, sir. Mhm.
Yes, sir, right? You like it, right? Now, then we have another type of, have you seen the mercury before? Have you seen the mercury before? You didn't
The
go to,
one in thermometers?
no, it's only in thermometer, right? Have you seen the whole cup of mercury before? I know, right?
Oh,
And
it's
you have
like
to go to the chemistry lab, right? Now, if you look at the mercury, right? Let's say I'm gonna fill the mercury in a container, right? They're gonna look like this,
yeah.
right?
Mhm.
HE. Now, in here, what does that mean? It means the cohesive force is larger than the adhesive force. So what does that mean? It means the force between the mercury and mercury is larger than the force between the mercury and water. Good, hello?
Yep.
Now, what should I say there? Now, we have two more sections, right? So I think I'm going a little bit fast today, right? So what we're gonna talk about that is next time is we're gonna talk about the surface tensions. And capillary effect, right? Capillary effect. Right, to conclude this chapter. Yeah. Now, what is survey tension, right? I think you probably see the survey tension before, right? So I'm going to show you this. So let me see here. Have you seen that before? You have a paper clips floating in the water? No?
Yes. Yeah, you have to fold them in a certain way.
Now,
Or-
it's something to do with the survey tension of the water on the paper clip, right? So it will have a survey tension force upward against the mg downward, the balance, than the water flow. And have you seen a dragonfly standing on the water? Or some insect, right?
Yeah, any water bugs sometimes they do that.
But even you see this, right? Well, you see this before? Hello?
Yeah.
No, I don't know whether there's survey tension, right? The Jesus is too heavy for the survey tension to support himself, I believe.
Yeah.
But I will explain it usually. I would tell the student maybe Jesus make the survey tension so large, it support him to walking on the water. Okay, anyway, and I'm gonna